All right, so this one isn't as bad as maybe they go or would make you to believe. So I haven't read the chapter this year yet. So I'm yeah. So I don't remember what the Dumas bulb is or what it looks like, but I feel like somebody would take it as an insult if you called them a Dumas bulb. But you know, you can go in the gym and try that sometime, see how it works. Um, But when I seen them tell me that the mass of the vapor is 0.846 and the volume is 354 centimeters cubed, that should throw off something where you're like, I think I know something I can do with mass and volume. Like what? Yeah, like density. And then they give you pressure and they give you temperature. And hopefully, since we just did the last problem, you might be like, oh, yeah. Okay. What is that? And why is it? Oh, dear. Do we have all the parts to fill in this equation? Yes, we do. So let's do that now. 0.846 grams divided by 354 centimeters cubed. Oh, snap. Wow. Yeah, you got to convert it to liters. Dadgummit. Okay. Hey, you know what? That's easy, though, because centimeters cubed equals milliliters, right? Yeah, and then if you just put a decimal in front of it, that'll make it liters. So let's do that. All right, and y'all are on it because without me telling you that, you're like, yeah, the gas constant has liters in it, so we got to be in liters, and that's good that y'all are realizing that. Okay, if we're working in torr, I think we're going to be doing the 62.36 thing again. Okay, temperature 100, so 373. And pressure is 752 torr. $70 something, maybe 73.9. Yeah, three significant figures is probably about right. And let's check out some units. Torrs, kelvins, liters, grams per mole. Yes. Does that seem like a reasonable molar mass? Yeah. Okay. So again, when you're attacking a problem like this, even if you're not familiar with the method, you might still be able to do whatever they're talking about. So there you go. By the way, if you go through the AP chemistry exam and don't get a question where you use the ideal gas law, I would be surprised. Okay. Let's see. So enriched uranium can be produced by gaseous diffusion of UF6. That sounds like a great factory to work in. Yes. Okay. Let's see. So suppose a process were developed to allow diffusion of gaseous uranium atoms. Calculate the ratio of diffusion rates for U-235 and U-238 and compare it to the ratio for UF6.
Yeah, I don't think we have the essay.
Yeah, it's in the book. If you read the book, you would see it. Okay, so we'll go back and look at that, but they want us to compare the rate of 235 to 238. Yes. All right, so let's did we learn an equation yesterday for doing that? We don't, but they want the ratio, don't they? No, it's not a mole ratio. Remember the thing we worked out yesterday where it was the ratio of the velocities?
Yeah. It's the root of m1 over m2 equals v2 over m1.
Yeah, yeah, sure, why not? I'll do that. That's how I wrote it. That's probably not how it's written. It's probably A over B equals B over A, but hopefully y'all are intelligent people, so you get the idea. All right, so what I'm going to do is I'm going to point out first to you that this is a ratio. And those are velocities, so those are the rates at which something moves. So this thing here is the ratio of rates. So it wants us to solve for this ratio. That means we don't solve for the individual. Yeah. Okay, so I want to know the ratio of 235. I think they're saying 235 over 238. So when I do the square root of the things over here, I'm going to do 238 over 235. And when I do that, not going to be a whole lot of difference there. 238 over 2. Okay, 1.00. Yeah, and really, I don't even feel good about reporting that to that many significant figures, but I'm going to go with it. It's not going to be off enough that that's going to be dramatically different. Now, I happen to have a copy of the book over here, so let's look. How much are these guys going to separate from each other, by the way, if that's the ratio? Not very much. So it would seem to me that you would have to, I don't know, maybe have a really long distance for them to travel, for there to be enough separation to really collect one over the other. And something about radioactive isotopes traveling long distances just bothers me, but, you know. All right, 10.8. And somewhere in here, chemistry put to work. Okay. There it is. All right, so if you have the fluorine added onto it, it's 1.004 instead of 1.006. Okay. So I guess the thing you could look at here is that when the fluorine is attached, that makes both of them heavier. So I guess maybe like the percent difference between the two is smaller. So there's less of a difference between how much they or how quickly they diffuse. Okay. All right. Anybody read that? There's some good reading in the book, y'all. Like I'm telling you, it'll help you if you'll read the book. Brown LeMay is one of the better chemistry textbooks, in my opinion. Like it's actually halfway interesting to read. It's really interesting to read if you're into chemistry, but not everybody is. All right, so arsenic 3 sulfide. That sounds nice too, doesn't it? Yeah, it is. Okay, arsenic 3 sulfide sublimes readily, even below its melting point of 320 degrees Celsius. The molecules of the vapor phase are found to effuse through a tiny hole 0.28 times faster, or excuse me, 0.28 times the rate of effusion of argon atoms under the same conditions. So what this is telling us is that arsenic 3 sulfide, AS2S3. So it's telling us that the velocity ratio here is 0.28. Yeah, that's the place where everybody gets stuck on this. Once you get here, y'all can do the math, okay? But the way this is stated probably doesn't immediately conjure up in your mind that all they're trying to tell you is that this one is basically that many times slower than this one. Okay. Now that we know that, what can we set this equal to since it's the ratio of the rates? Square root of the masses. And that's going to be which one over which one, since this is that one over that one.
Argon over arsenic.
Yeah. All right. Show. Is that important at all? I mean, it's no. Okay, they can tell you that, but that's just additional information. What is the molecular formula? Okay. Yeah, let's finish this problem. Okay, so here's the issue that the question that they're asking you when they say what is the molecular formula, I don't know that would conjure up the idea that you need to even use this equation to do that. And that's why you might be like, oh gosh, this is confusing. But what's one of the things that'll help you figure out the formula of something, or confirm the formula of something, if you know the what? Does the molar mass depend on the formula? Yes. So a lot of times, if they're asking you something about the molecular formula, that's a clue that you might need to find the molar mass of the substance in some way. And we have a way to do that here because this is the ratio of the molar masses of the compounds, or it could be a ratio of the densities of the compounds. Either one would work. But with that on here, well, we know the molar mass of argon is what, 40 point something, 39.948. Bless my heart. All right, so what we can do here is we can solve for x. So you're going to square both sides. Oh, dear goodness. Do we remember how to solve for a variable in the denominator? The quick way is just to swap it with whatever's on the left side of the equation. So all right, so 39.948 divided by 0.28 squared, 509.541. Now, this is going to be useful to us because we can take this and compare it. Now, up here, I wrote As2S3 for the arsenic 3 sulfide. And how could I confirm or possibly, not confirm that As2S3 is the right formula? What should I do with these? Find that molar mass. Let's do that. I'm going to pause the video. Okay, so As2S3, based on the name, is 246. The molar mass is, so what would you suggest probably is the actual formula of this? What would you have to do to this to get that molar mass? Double it, times it by 2. So it would be As4S6.
2 seconds.